All right, so we're the Mars Mavs. My name is Galen, Salle.
And I'm Julian, Crawford.
And we represent the University of Texas at Arlington. And this is our submission for the Mars Gemini competition.
Our mission objective is to first conduct human sciences in deep space. Then we need to assess the effectiveness of deep space habitats. And this mission is acting as a stepping stone for future missions. And this mission is also furthering the reach of mankind.
All right, so our mission profile will begin with a construction phase between 2017 and 2021, in which the modules will be developed and produced, and eventually launched into a 500-kilometer assembly orbit, after which there will begin a mission phase between 2021 and 2023, during which there will be a series of testing before the trans-Venus injection burn, because we'll be flying by both Venus and Mars during this trajectory, which I'll explain in a minute. There will be a total of 2 powered flybys, one at Venus and Mars, and the entire mission duration will be 592 days, with a return date on June 26, 2023.
During this section of our presentation, we're going to talk about our operations. First, we'll talk about the vehicle launch and the trajectory and why we chose those things. We'll talk about our crew health and how we plan to maintain that during the duration of the mission. And then we'll finish this section with mission experiments and what experiments we plan to conduct during the duration of our mission.
All right, so first is our launch sequence. We will be using a total of 3 Falcon 9 launches, as well as 1 space launch system. This is shown in orbit, beginning with our service module that will be developed, followed by the habitat module, and then our cryogenic propulsion module, and finally our command module.
For our mission trajectory, we chose our trajectory because it gave us competitive delta V. It offers us 2 planets that we can study during the duration of our mission. It also gives us additional time for research and development before our departure date. And our trajectory was developed by NASA's Jet Propulsion Laboratories.
All right, here's an overview of our trajectory, beginning at Earth, flying by Venus, Mars, and then back to Earth. Our first phase will begin with a trans-Venus injection burn of approximately 4 kilometers a second, which will be performed by our cryogenic propulsion module. Afterwards, we'll enter an interplanetary cruise phase, during which our spacecraft will be oriented with its engines facing the sun to allow our radiation shields to perform properly. And then this is a 140-day cruise phase, and then entering our Venus flyby.
After our Venus flyby, the spacecraft will reorientate itself with its engines facing the sun. And then we will enter our second interplanetary cruise phase, which is 180 days. Then we'll do our Mars flyby and then enter into our third interplanetary cruise phase, which is 272 days, where the astronauts will finally come home after that.
All right, and so for long-duration crew health, we have a number of things on this spacecraft. First of which is our environmental control and life support system, based on that of the International Space Station to complete their physical needs. They have an ARED exercise machine, which will allow them to, since they're in the zero-gravity environment, they will be able to exercise 2 hours a day in order to prevent muscle and bone atrophication, as well as a radiation shield, which is based off the main water supply, which will be between the astronauts and the crew quarters, or the sun and the crew quarters. Lastly, they'll have PCs, which will allow for human contact for their mental capabilities and to ensure that they have contact back home through the mission.
For our cruise experiments, we will measure our physical and mental capabilities of the astronauts. For the physical capabilities, they'll exercise on the ARED machine. The ARED machine is able to measure their vitals, and we can keep track of that during the duration of the mission. For the mental capabilities, they'll have puzzles on their personal computers that they can do, and we can keep track of that data also and see how their mental capabilities are being affected. We also will have a mission-long sleep study where when the astronauts go to sleep, they'll wear a cap on their head and it'll measure their brain waves, and we can keep track of that and see how deep space is affecting their sleep patterns. We will also have plant and microbiology tests. The most well-known of them is the Veggie module that is currently on the International Space Station. And then we will monitor radiation inside the spacecraft and outside the spacecraft for the duration of the mission.
All right, and then also, when they're approaching and during the flybys, they'll have a number of proximity experiments, the most important of which will be the Mars rover telepresence proof of concept, during which the communication systems will be directly linked to the rovers on the surface and allow for a proof of concept for future orbital missions which will also be using the telepresence and real-time exploration of the Mars surface through the use of rovers. In addition, there'll also be Cubesats, which will be launched at both Venus and Mars, and potentially just in orbit around the Sun, that could be used to monitor various systems or various environments. In addition, there will be a number of opportunities for public outreach, such as social media, so through Twitter, which a number of astronauts currently are using, as well as the Cubesats, which could be used as for international cooperation or through a university, through a number of universities' concept studies, as well as a 3D printer on board, which will allow for a number of like a design competition that would be where the public would be engaged and allowed to produce parts that could be produced on the station. As well, all of these would help for the STEM field.
During this section of our presentation, we'll talk about our vehicle design. We're going to go from top to bottom. We're going to start with our command module, which is also our Earth return vehicle. Then we'll jump to our interplanetary habitat, where the astronauts will spend most of their time during the mission. Then we will go to our service module, which holds a lot of our critical systems for the duration of the mission. And then we'll finish with the cryogenic propulsion module, which is crucial for getting the astronauts out of Earth's orbit and headed towards Mars.
All right, the first module is the command module and Earth return vehicle. This is a modified Dragon V2 spacecraft, which will have an upgraded flight navigation system and flight computer, as well as it'll be linked directly to the communication dish, which is located on our service module, which is a 30-meter dish connected via fiber optic cabling. And then finally, it'll have an external trunk, which will house the extravehicular activity supplies for when if the astronauts have to perform an emergency repair on the outside of the spacecraft.
Our entry, descent, and landing system, we have the Pika X heat shield, which was developed by SpaceX and is the successor to NASA's Pika heat shield. We also have the Super Draco retro rockets, which will decrease velocity upon re-entry, and then we will parachute into a wet landing.
All right, the next is our habitat, which is an inflatable design. This is based off of Bigelow Aerospace. This is a Sundancer concept, which is a step between the Beam concept, which is currently on the International Space Station, and the BA330. This is designed specifically for 2 astronauts for long duration, as opposed to the Bigelow Aerospace 330, which would be up to 6 astronauts. So we're not wasting as much mass. This contains the majority of our environmental control and life support systems, as well as our EVA tunnel, which will be connected to it, which will allow for the access of 2 Z1 spacesuits, as well as a small equipment airlock, through which the CubeSats can be launched, as well as small equipment.
We have our Cube satellites, which will be launched from our EVA tunnel. They will intercept Mars and/or Venus, and they are potentially developed by universities or space agencies. This is great because the universities or space agencies can help us decide which experiments that we can run at each of these planets.
All right, on board is a 3D printer, which is based on that, currently on the International Space Station. It'll allow us to have in-space manufacturing en route to Venus or Mars. That will decrease the total amount of spares and increase the likelihood that we could have a self-rescue in the event of an emergency. And it'll also provide on-demand services for either public outreach or, again, just if anything is needed on board, such as routine maintenance or something of this part that could be manufactured.
Air rejuvenation system. The oxygen is produced in OGS racks. The water is taken from the main water tank, and the oxygen is extracted, and the excess hydrogen is vented overboard. We have a carbon dioxide removal system that is a reusable zeolite bed that vents the carbon dioxide overboard once it's been saturated. And then we have a trace contaminants removal system, which is a charcoal filter that's in the ventilation system. And that's not reusable, but once it's saturated, we can take it out and replace it with a new one and store the saturated one.
All right. Next is our water recycling system, which takes in gray water and urine, which will be recovered in the water recovery system rack. It'll be, and then pumped directly back into the main water supply. We'll assume a 90% efficiency, although up to 95% efficiency has been seen aboard the International Space Station. During
Emergency situations, our command module is our safe house. It has 2 weeks of emergency rations, which include emergency water and emergency hydrated food so that the astronauts don't have to go into the main habitat and grab water from the water tank. We have 3 days of air rejuvenation, which is in solid state canisters. And we have emergency EVA supplies that are located in the EVA trunk that is connected to the command module. And we have a 3D printer that can print spare parts in emergency situations.
All right, the third module is our service module, which stores our long-term hypergolic propellant system, as well as our electrical system, heat rejection system, and our reaction control systems fuels.
For our hypergolic propulsion system, it's a helium pressure-fed system. We have monomethylhydrazine as our fuel and dinitrogen tetroxide as our oxidizer. That's a tough one to say. Try and say that one 3 times quickly. And then we have our Super Draco engines, which were developed by SpaceX.
All right, and for our electrical system, we're using gimbal triple junction photovoltaic cells in order to maximize the amount of efficiency, using 3 layers of different materials to capture different wavelengths. We're also producing up to 5 kilowatts of energy at minimum, even at the lowest solar constant whenever we're by Mars. This will be then stored in lithium-ion cells for up to 24 hours emergency power, as well as converted into a lower voltage before it's sent to our double redundant bus systems throughout the spacecraft.
We have the power system racks. This is my favorite part of the spacecraft. It's something I worked closely with. There's 4 symmetrical racks that house our power regulators and our batteries. They connect directly to the photovoltaic arrays. They slide out and they're easy for the astronauts to access outside the spacecraft. And they're modular and independent so that the system can keep running if one rack were to fail.
All right, and this is our power distribution bus, starting with our powers being generated in our photovoltaic array on our service module, and then regulated before being sent to either the lithium-ion batteries or directly to the main switch. And then afterwards, it's converted to a lower power before being distributed amongst the various buses and then to the individual systems that are needed aboard the spacecraft.
For our heat rejection system, it's derived from the International Space Station, and the heat is collected via water tubes that run throughout the entire spacecraft. The heat is then transferred to an ammonia loop that is in the service module. The ammonia then runs through the radiators that are outside the spacecraft, and the heat is rejected away from the spacecraft and the astronauts.
All right, and our fourth module is our cryogenic propulsion module. This is our last module, which burns rocket propellant 1 and liquid oxygen, which is turbopump pressurized, utilizing 2 Merlin Stage 2 engines developed for the upper stages of SpaceX's Falcon 9 rockets. It's the largest propulsion module and is the only module that requires a Space Launch Systems launch as opposed to a Falcon 9, and is what we use in order to break ties with Earth during our transvenous injection burn.
For our cryogenic propulsion module docking port, it connects the cryogenic propulsion module to the service module. It's a new docking port that we would have to develop in-house, but it allows modules about no more than 4 meters in diameter to connect to each other. It's less complex than the International Docking System standard, and because it only transfers power and data.
All right, and for our mission, we assume a $20 billion budget, which is estimated via the analogous approach comparing to the International Space Station. We looked at the various number of derived technologies that we're using from the International Space Station and SpaceX specifically, assuming that we're at tech readiness level of usually 5 or above for most of our components, with up to 9 on several of them. And so compared to the $150 billion space station, we assume $20 billion. We also looked at a number of alternatives for various components on our spacecraft, such as launch vehicles, especially with the Ariane 5 or the Delta IV. However, especially with the Delta IV, it would require up to 40 million additional US dollars per launch. We also looked at the HAB, which we looked at either an ISS-derived or a wet lab potentially, but we deemed that the International Space Station modules would have too much mass compared to the volume that we could be achieved via an inflatable. And additionally, we looked at the wet lab, but that would require too much on-orbit assembly, and so we assumed that for this mission it would be deemed too complex. Lastly, we looked at the Orion and Soyuz for the Earth return vehicle and command module. However, the Orion was deemed too complex and large for the mission that we needed, as well as the Soyuz was very niche of a market for low Earth orbit purposes.
In conclusion, we believe in this spacecraft and this mission because this is a spacecraft that can be designed now with little additional development needed. It's a low cost and simple mission using today's technology.
All right. Is there any questions? Yes, sir.
Yeah, I wanted to ask you the same one I asked the other group was thermal protection at Venus. I mean, have you gone through the numbers that you can?
Yes, we're able to release up to 10 kilowatts of energy worth of heat from the spacecraft via our radiator system. However, we're not able to calculate exactly how much we would be pulling at near Venus.
Yeah, what's your altitude above Venus?
Unfortunately, I'm not sure of that number off the top of my head.
Why did you reject hydrogen and also reject CO2 instead of reacting them with each other and recovering the oxygens as water and also producing methane?
We deemed that would be a little bit too much of additional development for the environmental control system, and we wanted to ensure that the safety of our astronauts aboard the station, where a Sabatier reactor could produce too much heat, and since we weren't sure of the calculations on that, we did not want to deem the risks involved.
All right, and thank you very much.
Thank you.